Okay, so just finish up that one. So we had gone to 7 power 4, and we said this 4, it's 2,401. And so we divide this by 15. What do we get?
Goes in 160, remainder 1.
Remainder 1. Okay, so once the remainder is 1, then we say this guy is equal to 1. What does it mean? The order of 7 is 4. Remember, for multiplicative, we are saying Gn. When Gn is E, then the order of G is N. So the 7 power 4, the G is 7, the N is 4, and we get the 1, which is the identity of the group. So that becomes the order of that guy. So nice. Very visible. Another one. Let's find the order of 13. What is the order of 13? The order of 13. So there are so many ways of going about this. You can still square the guy and see how many times it gets us. There's nothing changing. The same way we're doing 7, you can still go through the same one to get the order of 13. Or we try another option that involves the modulo. And you understand that if you write 13 in this group, it will be the same as -2 modulo 15. Meaning, it just makes sense to say, if I'm squaring 13, it's the same as I'm squaring this one. So if I cube this guy, the same as I cube this one. So let's see what happens if you cube a -2. It takes us to 4, is it? Remainder. So yeah, that is if I need to square the 13. So now we're getting the simplified version of the 13, meaning that when you say 13 squared, we expect the remainder to be 4, which is given by squaring -2. So we got the difference there from 15. Then this is 3 here. So if 3 will get 8. So I'm not yet there. So we extend, we say 13, 4, -2. So here we're getting a great action. 4 will give us 16. Now remember 16 is nice. So because the remainder here is what? The remainder here is 1. If we bring in 15 and divide, the remainder will be 1. So if the remainder is 1, then we have found what we're looking for. Right? So the order of 13 is going to be 4. Where you can also say, so even we use that for groups, we can also use it for independent elements. Like that. It just has to make sense. These examples are nice. I feel like if you get the understanding, it gets to be very, very nice. Look at Z10. Z10 will run from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So what's the order? So the order of Z10 is not debatable. This one is 10. And then the identity, because this is an additive group, so the identity here is 0. So you can start picking the orders of independent terms. Let's pick the order of 3. So saying multiply 3 by 1, it will give us 3.
Me, I'm behind there. How do we find the Z10 there? Are we not supposed to not to include the factors which has common factors? I mean the numbers which has got common factors.
No, for the additive. Oh, you mean when getting the order of 10?
Yes.
Okay, this thing is sleeping. I don't know. So when getting the order, since you're talking about 10, so say 2, 5, just 2, 5, is it? Yeah, just 2, 5.
Yes.
So the order would be 1, 2, 3, 4, 5, 6, 7, 8. So it will be 8. Yeah, the order will be 8. So the same thing there. You get confused me. Yeah. So it's 8.
So there we are not supposed to include 2, 4, and 6, right?
They must be factors of 10.
Factors of 10.
Okay, let's see. Let's see if we put 3, we couldn't put 6, we couldn't put 12. Oh yeah. Okay. Okay, no, in the when getting the when listing, there's no harm in listing them, but when getting the order, yeah, we need to exclude them also. So it won't be 8. Nice. Now we do the same one. Let's see how we get the order of 7 in Z10. What's the order of 7? So say 7, 1 is 7, 7, 2 is 14, 7, 3 is 21, 7, 4 is 28, 7, 5 is 35. So 7, 6 is 42. 7, 7 is 49. 7, 8 is 56. 7, 9 is 63. 7, 10 is 70. 70 divided by 10, 7, remainder 0. So the order of 7 is equal to 10. So it seems like all the primes, the easiest way of getting their order is multiply them by 10. That's when you get to know that. I mean, that's the easiest way you get a 0 as a remainder. Okay, what if you use the modulo approach? Would it yield the same result? Like here we are doing there, because if we say any modulo works for the multiplicative thingy mostly. But it could still make sense, because the modulo of this, let's see, the modulo of this would be 7 minus 10 would get -3. So for -3, the order of -3 is 10. So is the order of 7. So the modulo ones share the same order. I don't know if you understand what I mean there. Like the way we did to 13 that time. Or was it in here? Yeah. Here we got a modulo. Though it was u, but we got a modulo of that. So we got the -2. Instead of squaring 13, we were squaring 2 and getting the remainders. Until the time we got the remainder 1, then we knew that even 13 at that point, if we had to get the actual value of 13 to the power 4, 13 squared, it's a big number. 13 squared is 169, and then you multiply by 13 again by 13. So 169 by 169, a big number. But then when you do the division, the remainder will be 1. So I can easily use EC modulo -2 to see how I find myself with the other piece. So what must we take note of here before we read these examples is the difference between U and Z. Okay, so if I want U10, listing the elements, I'll list 1. My next one will be 3. I can't list 2 because 2 is a factor of 10. So I can't list 4 because 4 is a multiple of a factor of 10. So I can't list a 5. I can't list 6. So everything I'm listing here must be relative prime to 10. So my next number will be 7 and then 9. When you say relative prime, when I say 10 over, we list 1 because 1 is the identity in here. So each group must have an identity. But if I say 10 over 2, I'll simplify it to 5. If I say 10 over 4, I'll simplify it to 5 over 2. Meaning in its original state, it's not relative prime. If I say 10 over 5, I'll simplify it to 2. 10 over 6, I'll simplify it to 5 over what? Over 3. 10 over 8, I'll simplify it to 5 over 4. 10 over 9, it remains 10 over 9. So we pick such ones and we call them the relative prime numbers there. That's how we make, and that's so the order here will be 4. So the trick thing here is So if we said, let's see why we said the order of 15 was not 15. Because by listing initially, we're supposed to even say 1, no 3. The next one should be 2. Then 4. No 5. Okay. Then 6. Then 7. Then 8. No 9. No 10. Then
What
11.
about 6?
Then 11. Not 6, yes, because of the 3 there. So it's 1, 2, 4, 7, 8, 11, no 12, 13, 14. So what's the order? Here now, once you don't bring in any of those, the order becomes a direct thing. We easily, so this is U15. So if the order, just count 1, 2, 3, 4, 5, 6, 7, 8. So we say the order of this is 8. Simple. So what would be the order of U17? Because of the nature of 17, it looks like everything here will be listed, is it? Because we list 1, we list 2. The guy didn't have anything in common with any other. So all the elements, all the numbers will come back. So the order will be 17. That's the nature of the number. It's relative prime to every number, just like 11. I've lost my page. Okay, but for the Z, it will be a different story. Z just lists from 1 up to there. I don't care about being factor or what. Okay. So where are we? Okay, so we've gone as far as defining the order of the element and trying to get the order of elements. Then we can look at the definition that is bordered on the subgroup. That's defining a subgroup. Subgroup definition. The subgroup. What is a subgroup? Okay. So if a subset H, if a subset H of G, if a subset H of G is itself a group, is itself a group under the operation of G, we say that H is a subgroup of G. That's very basic. That's very, very basic. But it means a lot. So if I'm given a set, if I'm given Z4, and then I'm also given Z2. And now Z2 looks like a subset of Z4. So if I check Z2, it's a group under addition. Then I'm able to say that Z2, a subset of Z4, sharing the same identity as Z4. Is a group, but then it's a subset of Z4. So it will be a subgroup of Z4. I'll remove the subset and put subgroup. So it's a group in another group. The same way we identify that this is a subset of this set. It's the same way we'll say it's a subgroup of this group. We'll remove the set from both and put group and see what we remain with. So here the statement H is a subgroup of G. It can be denoted by, as if you are doing the less or equal. You can say H is less or equal to G. And so you mean it's a subgroup of that. And then, if we wish to indicate that H is a subgroup of G, but is not equal to G itself, then you just put H is less than G. So the same properties like we do with sets. Less or equal to, you mean there's a possibility that H can be G. That's the equal to part. But if you wish to emphasize that such a possibility is not there, then you just say H is less than G. So we understand what we're talking about. Such a subgroup is called a proper subgroup, just like a proper subset. And so the subgroup consisting of one unidentified element is called a trivial subgroup of every group. So every group has a non-subgroup, the subgroup of the identity only, with order 1. Because the key thing that you're going to notice in all the groups that you're going to study is that every group has a subgroup, has an identity element. And every subgroup of any group shares the same identity element with the mother group. So before, the first thing to check, if I want to check that this given subset is a subgroup of this G, my first thing to check is that does that subset have the identity element? If it has, is it the same as the identity element of G? If they're the same, I can go to check for something else, which will be which operation am I dealing with? Is it addition for both? Is it multiplication for both? Of course, the identity will tell you which operation for you to know that it's an identity. Okay. So in determining whether or not a subset H of a group G, one need not directly verify the group actions. So there'll be a theorem that will help us not to go through all the actions. So I think in the next class we'll start from there. We'll start from the subgroup criterion, and then we'll do examples of subgroups. And we'll do 2 more theorems before you look at the examples, then look at the examples of subgroups. And then start looking at the groups themselves now. The symmetric is the first one and the most important group. So that we end our class here. Tomorrow we have 2100 as we agreed to the alternative. So start by finishing the tutorial sheet and then maybe look at some notes or go straight to tutorial sheet 2.
So what about the assignments?
When is it due?
20 June.
Today is 9. Yeah. Okay. Next week we'll look at the assignment.
Okay, sir.
Okay.